You've had this as a vocab term in the last unit or so. Empirical formula means the simplest. Now, what do we mean by simplest formula? Simplest what? Simplest ratio. Whole number ratio. So maybe you want to add that in there. Simplest whole number ratio or formula. Because that's all a chemical formula is a ratio of how many atoms to other atoms that you have within those elements to get those charges to balance out and whatnot. We've already discussed. So here is our saying to help you remember this. Okay? You have it in your notes. I would encourage you to highlight what is in bold so that you can remember that. And that's what I would encourage you to try to not only memorize, but to be able to write down on your quiz on Wednesday as well as your test on Friday. So yes, as a reminder, we have a quiz on Wednesday. It's on empirical formulas and molecular formulas that we're talking about today and tomorrow. So here it is. It says, assume 100% of the sample, right? You're not going to have more than 100%, and all that you have equals 100% because it's what you have. So we're going to change our percent to grams for each element. Then our step 2 is we're going to find moles from the grams of each element. Then step 3 is we're going to find the smallest whole number ratio where we're going to divide by the smallest number of moles. Step number 3 is the step that people forget most. All right, that's the one that they forget most. And then step 4 is only if necessary. We'll kind of get there. We'll do a couple practice problems. You'll see what I mean by if necessary. So the saying goes like this. All right, it's mass to moles. Then it's going to be, I'm sorry, I already skipped a step. It's percent to mass, mass to moles, percent to mass, mass to moles, divide by small times to whole. So there's that little rhyme. Percent to mass, mass to mole, divide by small times to whole. Okay? That's kind of what we're doing here. Every single time you need to go through this process. If you skip steps, that's where things will get really difficult really fast. All right, it'll seem a lot harder than it needs to be. So let's just jump in to a problem. We'll kind of work out what it means to do each one of these steps. So page 8 in your notes. Here we go. Example number 1. So it says a compound is 78% barium. I'm sorry, not barium, boron. It's a Monday. Holy cow. 78% boron and 22% hydrogen. What is the empirical formula? So our first step, this is the most important step. We got to go from percent to moles. So make sure you are watching here. Watch very carefully. Do not even blink because this is the most important, crucial step. It's one of the most difficult things we do all year. All right, so here we go. What we want to do is we got to make sure that we are bookkeeping very well, being organized with our method. So we're going to write down, I've got boron, I've got hydrogen. So I've got 78%. So right now I'm just writing my given. I'm writing the information that I'm given. So here we go. Hardest thing, we've got to go from percent to mass. Are we ready? Wait, I've already messed up. Man, the struggle's real today. Let me just tell you. I don't know what it is. 78%. So here we go. 78 grams, 22 grams. Did we see that? Hardest step ever? Right there? That's it. Really? One little chuckle? That was a joke, guys. That's all it is. Step 1. If we're given percentage, we just change it from percent to grams, okay? Because think about it like this. We're saying that we have 100 grams here. All of our percentages are going to add up to what? 100. So we can still say it's a ratio that we're looking at, 78 grams, 22 grams. It's still 78% of our total mass of 100 grams is boron and 22% is hydrogen. So if you're ever given percentages, all you have to do is just take the percent sign and turn it to a grams. That's it. That's step 1. All right? Usually I get a little bit more of a laugh, but it's okay. Tough crowd on a Monday. It's a struggle, right? Anyway, there's our first step. Second step is to do what? Okay. How do we go from grams to moles, guys? We did this all last week. Divide by our molar mass. Yeah, we just do it, right? We just do it. Well, how do you just do it? You divide by the molar mass. So you can set up your T-chart. Grams on the bottom, moles on the top. This is where it's very important that you are making sure you know what element you're working with. What's our molar mass for boron? For boron? 10.81. And hydrogen's molar mass is going to be what? Okay, do the math. How many moles of boron will we have when we do the math? 7 point what? 2. Now, was it 7.2 even? Or was it like 7 point something?
7.21.
Right, remember, so this is where it becomes very important, guys. Do not round until the very end. If you start to round here early, okay, we're going to take these values and we're going to use them in another calculation. So if you round from the very beginning and you round every single time, your final answer could be way off and make this a lot more difficult than it should be. So it's 7 point what?
215.
215. That's good, guys. If you usually go out to like 3 or 4 decimal places, that should be good enough to where you're not going to run into any rounding issues. So, as you're going through these problems and our other problems that we did last week, 3 decimals is probably a good rule of thumb. You've gone far enough. Now, let me clarify that a little bit one step further. 3 non-zero decimals. So you may have something like this, even though that's 3 decimals, that's not good enough. Okay, it would have to be like 0.000952. Don't just round to that. Keep 3 non-zero decimals. All right, so don't worry about the zeros in there. Anyway, moving on. So this is moles of boron. When you take 22 and divide it by basically 1, what do you get? All right, so there we've done step 1 and step 2. So we've gone from percent to grams, and then we found our number of moles. All right, so when in doubt, go from mass to moles, guys, every single time. No matter what problem it is, if you're confused beyond there, if you get back to moles, you're going to get partial credit. So our step 3 now says we're going to divide all the mole numbers that we had. So we have 2 elements. We had boron, which had 7.215 moles, and we had hydrogen, which was 21.826. So what is the smallest number of moles we have here? Which element has the least amount? Boron, right? It's got 7.215. So what we're going to do is, when we get to this point, all of the number of moles that we have of all the elements, now we can compare them. Can I compare masses of different elements together directly? Why not? I see people shaking their head. Why do you think we can't do that? What's the big reason why, Alex? What do you mean by they're all different? Yeah, every single element has a different size atoms. So their masses inherently are going to be different. So that's why we don't use grams to compare. That's why we always, what's the link between mass and particles? It's moles. Moles is our unit that we can compare directly to one another. We take that mass feature out of it, right, where we're taking the size of the atoms, and we're just going to how many atoms we actually have, or how many moles we have is that counting unit. All right. So once we get everything to moles, now we're looking for the smallest to start looking for that least whole number ratio. So I'm going to divide every single element. In this case, I've got 2 by 7.215 moles. On the top, what's my number going to be? That's easy math. Notice, do we have a unit here with this number? No, because moles have been canceled out. And that's a good thing. We don't want to have a unit here because we've gone from percent to grams. We went from grams to moles, and now we're dividing by the least number of moles. So we're just getting a number because, again, these numbers we're getting, this is our ratio. Ratios aren't going to have units with them. Now, when we take 21.826 and we divide it by 7.215, what do you come up with? What's that? 3.02. So what's that basically? 3. So our ratio here, guys, is for every 1 boron that we have 3 hydrogens. This tells us our formula. These numbers that we get here after we divide by the least number of moles, those are our subscripts for our formula. So our formula here is going to be BH3. BH3, boron trihydride. Now, the last step in our problem, so we did percent to mass, mass to mole, divide by small, the last step of times to whole. We don't have to do that here because our numbers, after we divided by the smallest number of moles, were even. All right, they were whole numbers. We only do that last step when we have to multiply to get to a whole number. We'll see a problem here like that in just a second. Questions about this process? Is it anything completely brand new? We've been doing the steps all along. The only new thing is, hey, we've got to recognize what's the smallest number of moles. And that is the step that most people will forget. Or people who struggle with it, they often forget to do that. Let's do another example. All right. So, example number 2 says, analysis shows a compound to contain 26.56% potassium, 35.41% chromium, and 38.03% oxygen. Find the empirical formula for this compound. What's our first step? What's the saying say? Percent to mass. So write down each element that we have. We've got potassium. We've got chromium. We've got oxygen. Here's just a little side note. Typically, the order that they give them to you in, that's going to be the order of your formula. Typically. All right, so like this one, it's going to go K, then CR, and then O. That's kind of how we'll write our formula out. All right, so I've got 26.56. Do I really even need to write the percentages down, guys? Absolutely not. So you can just, if you want to just kind of skip that one step, recognize it in your head and do it in your mind, that, oh, percent just becomes grams. So I'm just going to write it down as grams. So then I've got 35.41 grams of chromium. And then I've got 38.03 grams of oxygen. So we've already done percent to mass. Now what do we have to do? Mass to moles. Go ahead and get the number of moles for each element. 0.679 moles for potassium. How about chromium? Somebody different. 0.681. And oxygen? 2.377. All right, so we've gone from percent to mass, and then we've gone to moles. What's our next step once we have moles? So percent to mass, mass to mole, divide by small. Which one's the smallest? Yeah, potassium. So we're going to divide by 0.679 for each of them. 0.679 moles. 0.679 moles. Obviously, potassium's pretty easy. That should just be a 1. Now, 0.681 and divided by 0.679, guys, is basically going to be what? 1. It's like 1.00 something or other. Now, when you do 2.37 divided by 0.679, what do we get? 3.5. Okay, 3.5. I'm going to go on to my next slide, but we see something up here. So K was 1, CR was 1, oxygen was 3.5. So our formula, our little saying said percent to mass, mass to mole, divide by small, times to whole. So again, what do these numbers show us? We just talked about it with our last one. What does this give us?
We can multiply by 2 to have the smallest ratio of last one.
Right, so remember, this is all in all, to get to these numbers here when we divide by our smallest number of moles, is a smallest ratio. But what does our empirical formula say? It's the smallest whole number ratio. So right now we have a ratio, 1 to 1 to 3.5. All right, and this is one step that people will mess up as well, and it just messes up everything else. We want to keep it in that same 1 to 1 to 3.5 ratio. If I were just to round this to the nearest whole number of 4, is that the same ratio? Absolutely not. Now it's a 1 to 1 to 4 ratio. So this is why we multiply to get to a whole number. Okay? So what's going to be the easiest way to get 3.5 to a whole number? Multiply by, like Tony said, 2. But if we multiply this by 2, we have to multiply all of them by that same number. So times 2, times 2. So we get 2, 2, and 7. So what's my formula going to be? I'll give a prize to whoever can tell me the correct name of this compound by raising your hand. Right there. So, here are the numbers that you want to remember. And if you think about it, guys, if you just think about fractions, okay, what's 0.25 in fraction form? A quarter. What's 0.75? What's 0.33? 0.66? 0.5. Okay, another one you might see is if it's like 0.2, what would that be? 1/5. So really, if you think about it in terms of fraction, the number you're going to multiply by to get it to a whole number, guys, is going to be that bottom one to cancel it out. Okay? So this is something you've got to just know how to get it to the nearest whole number. I don't know. I'm going to be looking, like I said, I'm going to keep digging into those old Regents exams. I don't know what kind of problem they're going to give you. If it's going to be another crazy one, I would imagine that at this level, they're going to keep it to 0.25, 0.33, 0.5, 0.75, 0.66, maybe 0.2. Okay, they're going to keep it fairly simple and not be something crazy. We have to multiply by like 14 or 7 or something like that. Okay. Now we're going to do a lab later in the year where you may have to do something like this. Lab data is different than like a theoretical problem. All right. So if you get lab data that's crazy, yeah, that could happen. But we're going to keep it simple here. Tony, as you continue to work, I'm going to start putting the answer up here. I'm going to start working it out so you can check your work. Remember, sig figs will play a part. Well, not really in this. One thing where to keep as many sig figs, though, just try to be consistent throughout. Remember, don't round early. All right, how many moles for calcium did you come up with? And phosphorus. All right, so when we get to our moles, remember, don't skip this step. What I've seen a lot in the past with my students over the years is that when they get to moles, that's when they start trying to multiply to get to a whole number. Okay? You've got to go through it. Say it to yourself. Mass to mole, percent to mass, mass to mole, divide by small. Don't forget that, because again, that's where we get the ratio from. This is not really a legitimate ratio. This would just be a ratio of masses. Okay? Remember, we already said that mass you can't compare from one element to another because they have different size atoms. So divide by the smallest, which is going to be 1.098. That's going to be 1.098 moles. This is going to be about what for calcium? 1.5. Look at that. Now, what are we going to multiply by to get to a whole number? Times it by 2. Am I just going to multiply calcium by 2? Absolutely. If you do it to one thing, you got to do it to all. So then we're going to multiply that by 2 as well. And it's going to get 2. So what's my formula going to be? Ca3P2. What's the name of that compound? Calcium phosphide. All right, calcium phosphide. Questions? Try the next one as well. When you do the math for sodium, how many moles of sodium do you get? 408? 408. Sulfur? And oxygen? So which one are we going to divide by? Smallest would be sulfur, so 0.706. That's going to be about 2. This is going to be 1. And this one's going to be about what? Okay. So what's our formula going to be? There it is. Sodium sulfate. That's our process. Again, is it really anything super brand new, guys? From what we've been, no, it's doing that same basic teacher. It's a one-step conversion. The new step is to recognize, hey, we're going to get a ratio, so we're going to divide by the smallest number of moles, because moles are what we can compare. And this is going to be a theme that we will use all year long, comparing moles of a substance to another substance. Okay? Questions?
Why is iron 3 oxide written on the wall?
Oh, I don't know. Here's your homework. Finishing page 9. Go for it. You got the rest of the period to work.